Hi there, folks. Today we're looking at the midterm review, and I am the amazing Mr. Jansen, so here we go. If we take a look at this first one, when we're graphing things, the first thing we need to do is recognize, first of all, what type of function it is, and then from there, we need to recognize the format of that function. So this first one is a linear type of function, or a linear type of graph, really. It's in the format x equals a number. And whenever we have x equals a number, that is the format for a vertical line. So I go to x on the, 3 on the x-axis, which is right here, and I draw a vertical line. And the reason for that is when you think about all the ordered pairs on this line, every single one of those ordered pairs has an x value of 3, hence x equals 3 is a vertical line, okay? If I look at the next one, once again, this is a linear equation, and it is in the standard form. And whenever we have something in standard form, the easiest way typically to graph is going to be find the x and the y-intercepts. To find the y-intercept, I plug a 0 in for x. So if I were to plug a 0 in here, and hopefully you can solve this in your head. If you had the equation 2y equals 6, you would divide each side by 2, and you'd find out that y equals 3. And so that's the ordered pair 0, 3. I plugged in a 0 for x, and I found out then that y equaled a 3. And now to find the x-intercept, I plug a 0 in for y. So now I plug a 0 in for y. And once again, hopefully you can solve that in your head. You divide each side by the -3, and you get a -2. So it's the ordered pair -2, comma 0. You got a -2 for x when you plugged a 0 in for y. And now if I plot those 2 points, 0, 3 is right here, -2, 0 is right here. I can even see the slope of this line now. It's up 3 over 2. And I could continue that pattern to draw a nice, accurate line here. Okay? If I look at this next one, once again, this is linear, and it's in the format y equals mx plus b. It's in slope-intercept form. So here, this guy is the y-intercept. So I go to -3 on the y-axis. And then this one right here, that is the slope. So that's telling me to go up 2 over 1. So I go up 2 over 1, up 2 over 1 again. And I can do that in each direction and then draw my line. Okay? If I look at the next one, this is technically direct variation, but it's still in the format y equals mx plus b. There's just no b value written, which means it's a 0. So there's a plus 0 here. So the y-intercept is 0. So I plot a 0 on the y-axis. And now the slope is -4. Again, that's like -4 over 1. So that's down 4 over 1. Or I could go up 4, back 1. Okay? And then once again, draw my line. So look at this one. Once again, standard form. This is standard form. So I'm going to do the x and the y-intercepts. If I plug a 0 in for y and solve for x, I find out that x equals 4. So that's the ordered pair 4, 0. Likewise, if I plug a 0 in for x and solve for y, I get a -1. Y equals -1. So that's the ordered pair 0, -1. And now that's enough information to graph this thing. I plot those 2 points, 4, 0, 0, -1. And I can even see my slope. It's up 1 over 4 or down 1, back 4 if I wanted to fill in a couple more ordered pairs. Okay? This one is in point-slope form. So this is a linear equation. It's in point-slope form. And remember, point-slope form is this one. It's y minus y1 equals m times x minus x1. Where that x1, y1 is the ordered pair that we're going to start with. And notice the minus signs that are kind of built into the formula here. Those kind of tend to make what we're seeing in the actual equation the opposite. So in other words, right here, this is the opposite of the x value for my ordered pair. This is the opposite of the y value for the ordered pair. And so the ordered pair ends up being +1, -2. It's the opposite of each of those values. The x value is with x, the y value is with y. And so I plot that point, 1, -2. And now once again, this guy right here, this is my slope hanging out in front of these parentheses. That's the m. So I go down 3 over 2. So down 3 over 2. Or up 3, back 2. I draw my line and that's it. Okay, point-slope form is the one that students tend to forget. And if you do forget that, you could potentially here use slope-intercept form by distributing the -3 halves and solving for y, subtracting the 2. All right, but it's much, much easier to identify this as point-slope form, find the point, and then use the slope. Okay? If we look at these guys are absolute value equations, which are kind of linear in nature, all right? But we're following a new format here. And so the format for an absolute value equation is this one. It's y equals a times the absolute value of x minus h plus k, where hk is the vertex of this thing. And notice there's a minus sign built in with this h, which means when I see that h value, I'm actually seeing the opposite of the h value. But notice this one doesn't have a minus sign. So when I look at this equation, I'm seeing the actual k value, not the opposite. All right. So in other words, for this first one, the vertex on this one, well, right here, that's the opposite of the x value. So the x value is a 1. But then right here, this is the actual k value, which is 3. So I only take the opposite of the thing that's inside with x. Okay. So that's the vertex. And then the a value, this value out front, kind of acts like the slope, but also tells me whether this v is going to open up or down. Okay. And so because the a value is negative, this one's going to open down. And I'm going to use that to kind of like slope. All right. Generally like slope. And here's what I mean. We'll plot that vertex 1, 3. And now I want to open down with a slope of 2, which is like down 2 over 1. Okay. And what I've actually drawn here is a slope of negative 2. I'm going to draw a slope of positive 2 in the other direction by going down 2 over 1 in the other direction. I'm creating this v with generally a slope of 2. Really, it's a slope of positive 2 and negative 2. All right. But I'm doing it in each direction just to make sure that this thing forms a downward facing v. Okay. And you could generally say the slope is a negative 2 also. Really, you're doing both versions of the slope. We just have to make sure that we do that in each direction, that we're graphing this v, and just make sure the v opens in the right direction, okay? If it's supposed to open up, make it open up. If it's supposed to open down, make it open down, okay? This guy, same kind of thing. This is the opposite of the x value. So for the vertex, that's going to be a negative 3. But then over here, this is the actual y value. So that's a negative 4. And now once again, I look at the a value for this one. I don't see anything written. That means there's a 1 out front. And it's a positive 1, so this thing opens up. And I'm going to use that one kind of like the slope. All right. In general, it's like the slope. It's not exactly the slope because I'll actually do a slope of positive 1 and negative 1. I'll do that 1 in each direction. So now I plot this negative 3, negative 4. And I'm going to open up with a slope of 1. So up 1 over 1 in this direction, but then up 1, back 1 in the other direction. Notice I have a slope of positive 1 and negative 1. I'm just ensuring that this v opens up. And then when I look at this guy, once again, I'm going to do the vertex here. The vertex on this one, opposite of this guy is the x value. That's a 1. This guy is the actual y value, so that's a positive 4. And now once again, I look at the a value here as a 1/3, so this one's going to open up. And I'm going to use that 1/3 kind of like the slope. Let's see, 1, 4. And then a slope up 1 over 3, but I have to do that in each direction. So I actually do a slope of positive 1/3 and negative 1/3 just to make a v that opens up. And that's it. If I look at these guys, I want to write the equation of the line. And this time it said to write the equation in slope-intercept form. So that's the y equals mx plus b. And here's the thing, we don't typically start with y equals mx plus b. The format that's easiest to write equations in is a point slope form. And so that's typically what we'll start with, all right? So I have to gather information. I need the slope, all right? And if I want to go right to slope-intercept form, I need the y-intercept, all right? If I don't have the y-intercept, if I'm given the slope and a point, I'll use point slope form instead. So if I look at this first one, it says write the equation in slope-intercept form of the line that's parallel to y equals 3x minus 1 and passes through the point 1, negative 2. So if I want to be parallel to this line, so this line that's written here is some line that, that's not the line that I want the equation of. That's some other line that I just happen to want to be parallel to. Okay. And so the only thing that concerns me with this line that I have the box around here is the slope. The slope of this particular line is 3. And so the question is, what should the slope of my line be if I want to be parallel to that line? Okay. And so parallel lines have the same slope. So if I want the slope of the line that's parallel, I also want a slope of 3. Okay, but now it's important to understand that I am essentially done with this equation. The only thing that I cared about from that line was that I was going to be parallel to that line. If that line had a slope of 3, my line's going to have a slope of 3. So now I want the line that passes through this point and has this slope of 3. Okay, and so as I look at this thing, I can't go right to slope-intercept form because I don't have the y-intercept. I don't know what b is. I have some other point on the line. So what I have is the slope and a point. I'm going to write this in point-slope form. And in point-slope form, remember I do the opposite of the x value over here, so I'm going to put a -1. I do the opposite of the y value over here, so that's a +2. And then the slope goes out front here. That's a 3. And so the equation of the line that I'm looking for is this. It's y plus 2 equals 3 times x minus 1. That is the equation of the line. It's just not in the format that I was asked to find. So to put this in slope-intercept form, I'm going to distribute this 3. And then I'm going to subtract that 2 from each side. And there it is, slope-intercept form, y equals mx plus b. Okay? If I look at the next one, same kind of deal here, but this time I want to be perpendicular to this line. So once again, the line that's given here is this guy, but I want to be perpendicular to that line. So this line has a slope of 1/2. And if I want to be perpendicular to that line, so I want the perpendicular slope. Remember, the slopes of perpendicular lines are opposite reciprocals, so I have to change the sign and flip it. So instead of a positive 1/2, I'm going to do a negative to do the opposite. And instead of a 1/2, I flip it, so I do 2/1, which is a 2. Okay, so my slope is going to be a -2. And once again, I'm done with this equation. That just helped me find the slope of my line. And now I want to pass through this point. So once again, I'm given the slope and a point. I'm going to go to point-slope form. Okay, y and then the opposite of the y value, so -3 equals m, which is -2, and then x, and the opposite of the x value is a +4. Okay, and now from here, I want slope-intercept form, so I'm going to do the same couple steps. I'm going to distribute. And then I'm going to add that 3 over to the other side. And there it is, done and done. Okay? If I look at this one, it says write the equation of the line in slope-intercept form that passes through the points 1, -2, and 4, 10. And so once again, I start off the same way, but this time, to find the slope, I actually have to do my slope formula. So for this particular example, I'm going to do y2 minus y1 over x2 minus x1. And just be careful with your signs here. That becomes a positive 12. This becomes a 3. And when I divide, that gives me a 4. Okay? And now from here, I'm going to simplify this thing. I'm going to plug this into point-slope form. And point-slope form this time, because I have 2 different ordered pairs, I could use either one of these. It doesn't matter which one. Maybe I'll choose the first one here, just because the numbers are a little bit smaller. So y, and then the opposite of the y value, so +2, equals m. And then the x and the opposite of the x value, so -1. And now from here, I can simplify and then solve for y. So I'm going to distribute that 4. And then subtract that 2 from each side. And that's it. Okay, so we're just putting the thing in point-slope form and then rearranging it from there. Okay. On this one, it asked me to find the x and the y intercepts. And so for that, when we're graphing these things, this is typically how we find the graph of this, is by finding the x and the y intercepts. But sometimes students won't necessarily do that. So we still need to have that skill. And so once again, you should be able to do this in your head. But to find the x-intercept, I plug a 0 in for y. If I plug a 0 in for y, I literally have the equation 4x equals 20. We'll solve for x, divide each side by 4, and I end up with an x equals 5, which of course is the ordered pair 5, 0. I got that 5 when I plugged a 0 in for y. Okay? And now I go again, I say, okay, well, now I want to find the y-intercept, so I'm going to plug a 0 in for x. And once again, I have the equation negative 5y equals 20. I'm just going to solve that. I would divide each side by negative 5, and I'd find out that y equals a negative 4. Okay? And of course, that translates into the ordered pair 0, negative 4. I got that negative 4 by plugging a 0 in for x, so it's describing an ordered pair. Okay? So this is the x-intercept, and this one over here is the y-intercept. I should scoot that over so I can show that. Okay? To find the x-intercept of any equation, you plug a 0 in for y. To find the y-intercept of any equation, you plug a 0 in for x. Okay? For these guys to determine if the following represent a function, use a graph if necessary. And so remember, for something to be a function, it means that every input has to have exactly one output. And so as I look at this first one, just a set of ordered pairs, I look for inputs that have two different outputs. If I find an input that has two different outputs, an x that has two different y's, then the thing's not a function. Every input, every x has to have only one y. And so as I look across this thing, I make note of these two ordered pairs right here. In this one, I have an input of negative 1 that gives me an output of 1. And in this one, I have the same input of negative 1 that gives me a different output of positive 5. Okay? And so this one is not a function because that one input of negative 1 has two different outputs. Okay? So no, this one is not a function. Okay? If I look at the next one, I would look at this and say, okay, does every input have exactly one output? The easiest way to think about this one is just think about the graph. Because this is an absolute value, that's going to be a v when I graph the thing, and really it's not written quite right. You know, there's a 1 out front, but then this x would technically be written as like x plus 7, all right? And here's the thing, the actual vertex here doesn't really matter that much. The vertex on this one is a negative 7 comma 0. And this one does open up and has like a slope of 1. And so if you kind of drew a quick sketch of this thing off to the side, negative 7 zeros here, and it opens up with a slope of 1. Well, now we use our vertical line test. Remember, the vertical line test tests each input to see if there's two outputs. So as long as a vertical line touches one point at a time, it's showing me that every input has exactly one output. If a vertical line touches 2 points at once, it means that the input that I'm testing at that moment has two different outputs. And so when I look at this, if I were to pass a vertical line across this thing, it touches 1 point at a time. So if you visualize a vertical line passing across that, touches 1 point at a time. So this one is a function. Okay. And really, when you think about it, wouldn't every absolute value function be a function? Okay. So I'm going to say yes, fun for that one. Okay. But every absolute value, no matter what kind of v I draw, whether it opens up or down, it would only not be a function if the v was sideways, and that's above our pay grade right now. We haven't learned how those graphs would manifest at this point. Okay. If I look at the next one, same kind of thing. If you visualize a vertical line being passed across this thing, so here's a vertical line. If you imagine dragging that across here and visualizing, would it touch 1 point at a time? The answer is yes, it touches 1 point at a time, so this one's a function. Okay. Having a graph is probably the easiest way to determine if something is a function, because the vertical line test is by far the easiest method for determining these things. Okay. This one, same kind of thing. When I look, this is point slope form of a line. This is the ordered pair 3, 2, and then the slope is a negative 1/2. So once again, if I kind of think about the graph of this thing, let me put some tick marks on here. Oh, there's the ordered pair, and then I have a slope of negative 1/2, so it's down 1/2. And I would draw the line. And here's the thing, it doesn't really matter that much in terms of the accuracy of my graph here. Any line is going to be a function. They're all going to pass the vertical line test except for actually a vertical line. And so because this is not a vertical line, and that's all I need to know from this graph, it's going to pass the vertical line test. So yes, this one's a function. Okay. Almost all lines are functions unless it's a vertical line. Okay. When I look at something like these guys, it says state the domain and range this time. And it says to sketch a graph that might be helpful. If necessary, you can sketch one. And so again, when we talk about domain and range, we're just asking ourselves what values are represented, okay? What X values do I have data for? What X values exist on this thing? And so when I look at domain, I literally just look left and right on the function. I say, hey, how far left and right does this thing go? And so when I look, this graph exists all the way to right here at -5, right? And then going the other way, it exists all the way to +5. And so I'm just asking the question on the x-axis, or in terms of the x values, where does the graph actually exist? Where do I have something drawn? And I have something drawn from -5 all the way to +5. And there's something drawn all the way in between there. Like here, there's a piece drawn right here at -2. And there's a piece drawn right here at -3 and a piece drawn here at -4 and all the values in between. I'm just asking, where am I drawing this graph left and right? And the answer is I'm drawing it from -5 to +5, okay? And so now we just kind of have to translate that into math speak. We'd say, oh, well, the x value, so I say x such that, I'm going to tell you that x goes from -5 to +5. And I do that by drawing this compound inequality. Say x is greater than or equal to -5, but less than or equal to +5, okay? That's just the math way of saying, hey, it goes from -5 to +5, okay? Range, same kind of thing, except I'm looking up and down. And so I ask the question once again, where does this thing exist up and down? Well, it exists from -3 to +3, and all the values in between exist somewhere, right? And so I would say, once again, y such that. And now when I define that y value, I'll use another compound inequality. Greater than or equal to -3, but less than or equal to +3. And that's it. If I look at the next one, this is function notation. Remember, f of x is the same thing as y. This is like saying y equals x plus 5, okay? And so once again, if I think about the graph of this thing, the graph might be helpful. I've got a y-intercept of 5 and a slope of 1. Well, there's the graph of this thing. And keep in mind, those arrows mean the pattern continues forever. This thing keeps going up diagonally forever and keeps going down diagonally forever. And so as I look left and right, on this graph, I ask myself the question, how far left and right does the thing go? What values exist left and right? And the answer is all of them. This thing goes left forever and right forever, so all of the values exist. So I say x such that, I'm just going to say x is all real numbers, okay? Every x value exists. And then as I look up and down, once again, if I look up and down, the graph goes up forever and it goes down forever, so every y value exists on this graph, okay? It covers all of them. So I'm going to say y such that, that's all real numbers as well. And once again, when you think about lines, almost every line has a domain and range of all real numbers, okay? The only ones that wouldn't would be a vertical line, would only cover one x value, and a horizontal line would only cover one y value, okay? It would still go forever in the other direction, though, okay? If I look at this guy, same kind of thing. Let's think about a quick sketch of the graph. Well, this one is an absolute value. This is going to be a v. And so if I think about this v, this has a vertex of -2, 4. Remember, opposite of this guy, but this guy just as it is. And this one opens down with kind of a slope of -1. And so let's draw a quick sketch of this thing. Ready? Let's see. -2, 4. 1, 2, 3, 4. That needs a semi-accurate. This one's going to open down with a slope of 1 in each direction. And so now when I ask myself that question again, left and right, how far left and right does the graph go? Well, that arrow means that it keeps going left forever, and the arrow on the other end, this guy right here, keeps going left forever, keeps going right forever. So the domain, once again, is all real numbers. So x such that it's all real numbers. But this time when I look at the range, when I look up and down this time, well, it doesn't go up forever, right? See, when I look at these arrows indicate that it goes down forever, but it doesn't go up forever. It only goes up as high as +4. So in other words, this graph exists from +4 on down. And so I just have to translate that into math speak. And so as an inequality, y such that I would say, oh, y is less than or equal to 4, okay? That's how we say all the values from 4 on down. We say y is less than or equal to 4, okay? Because that means 4 or less. And that's it. We're just looking at where does the graph exist? Where does it exist left and right? That's the domain. It's the x values that exist, okay? Where does it exist up and down? It's the y values that exist, okay? If I look at this guy, it says evaluate the expression y plus x to the second power plus 5z times w. Given x is a 5, y is a 6, w is a 40, and z is a 7. And so for this one, I just plug it in, okay? So y is a 6 plus x is a 5 squared plus 5 times z, which is the 7, times w, which is the 40. Okay, and now I'm just following order of operations for this one. I start inside the parentheses. In these parentheses, 6 plus 5 is an 11. And now I would do exponents. The exponent here, that's a 121. Next, I do multiplication, and multiplication can be done in any order. I could do the 5 times 7 and then times the 40, or I can do the 5 times 40 and then times the 7. Really, whatever is easiest. And if you're using a calculator, I guess doing it anyway is easy. And so for this one, I end up getting a 1400 here, okay? And now lastly, I add those together to 1521. And one of the things that you should make note of here is, one, yeah, we want to follow order of operations, but two, whenever you plug things in, use parentheses. Make sure you retain the fact that this is multiplication here when you plug those values in, okay? If we look at this guy, an absolute value equation, if I want to solve an absolute value equation, remember I have to split this into two equations. The absolute value is the distance from 0. In other words, it says that, hey, 3x plus 6 should be 12 units from 0. That's what this is saying. Well, that means that the 3x plus 6 could equal a positive 12 because that's 12 units away. Or the 3x plus 6 could equal a negative 12. Okay. And now I solve each of these the same way I've always solved things. I work backwards through order of operations. I undo operations as I go. So here I subtract the 6 from each side. That gives me a 3x equals 6. I divide each side by the 3. And I get x equals a 2. And now I have to solve the other one. I subtract the 6 from each side. That gives me a 3x equals a negative 18. I divide each side by the 3. And I get x equals a negative 6. And those are my two answers. And typically with absolute value, you can plug those back in and check them. Every once in a while, we'll get extraneous solutions with absolute value. But typically that comes into play if the absolute value equals a negative because it's going to be no solution. Or if I have another variable on the other side, sometimes I'll get extraneous solutions, okay? If I look at this one, this is a system of equations. So to solve this system, I use substitution or elimination. When I look at this, because everything's already lined up, the x's, the y's, equals, number, all lined up. And when I look, the y's are already additive inverses. I'm going to use elimination for this one. I can go right to adding these two together. And when I do that, here I get a 5x. Well, here the x or the y's cancel completely, and it equals a 10. And now I finish solving the equation that's left. It's just a linear equation. I divide each side by 5, and I get x equals 2. Okay, I'm not done yet. I have to plug that back in, and I can plug it into either one. I'll plug it into this one. Once again, use those parentheses when I plug stuff in. It saves me some headaches in the long run. And now I solve. I subtract that 4 from each side and divide by the 3. So I've got y equals a negative 1. And a lot of times when we solve a system of equations like this, we're going to write it as an ordered pair. So I'm going to write it as the ordered pair 2, negative 1. Okay? If we look at these ones, it asks us to solve for b. And these are literal equations, meaning that we're kind of just rearranging these things. So on this one, if I want to solve for b, I have to ask myself, what's happening to b? Well, b is right here. And to that b, we're adding an mx. So to undo what's happening to b, I have to subtract an mx from each side. So I'm going to subtract that mx from each side. And I get y minus mx equals the b. And now b's by itself, that's it. B equals y minus mx, and that's it. Done. If I look at the next one, I also want to solve for b. This time it's a capital B, which doesn't really make a much of a difference. But the first thing I notice is that fraction. So I'm going to get rid of the fraction just like I would in any other equation. I get rid of the fraction by multiplying each side by 3. And when I do that, I end up with a 3v equals b times h. And now to solve for b, I have to undo multiplying by that h. So I'm going to divide each side by the h. And so I find out that b equals, that's a 3v over h. And that's it. Okay, so solving those literal equations, we're still going backwards sort of operations, undoing operations as we go. But sometimes there's not as many numbers and simplifying involved. It's all variables. We leave it literally in terms of the operations. So look at this one. Brenda's school is selling tickets to a spring musical. On the first day of ticket sales, the school sold 3 senior citizens tickets and 9 child tickets for a total of $75. And second day is $67 with 8 senior citizen and 5 child tickets. And we want to know the price of each. So the thing I don't know is I don't know the price of each. So I'm going to call it X for the price of the senior citizen tickets. And I'm going to say Y is the price of the child tickets. Okay. And so that first day kind of breaks down like this. It says there's 3 of the senior citizen tickets plus 9 of the child tickets equals $75. And normally I would pick better variables here. But for like senior citizen, I didn't want to use S because it looks too much like a 5 sometimes. So pick variables typically that make sense or that are easy to work with. The second day looks kind of breaks down like this. It was 8 of these plus 5 of these equals a total of $67, okay? And then from here, you could use substitution or elimination for this one. Because things are lined up pretty nicely, elimination might be nice. The first equation there is also really easy to solve by substitution because you can X by itself. And so there's advantage and disadvantage to each. With elimination, yeah, everything's lined up, but the values are going to be really big because I'm going to have to multiply by some pretty big numbers. So I'm actually going to opt for the substitution this time. So I'm going to take this first one. And I noticed that everything's divisible by 3, so it's not going to be bad to solve for x. Okay, so I'm going to subtract the 9y from each side. And if you choose to do elimination on this one, that is fine as well. All right, and hopefully you get the same answer I do by the end. Now I'm going to divide by the 3. And again, if I looked at this and not everything was divisible by 3, I wouldn't be doing the substitution method here because I'd end up with fractions. Okay, and now I'm going to plug that into the other equation. So I have 8 times x, which I can replace with the negative 3y plus 25. And now I can simplify this thing. I'm going to distribute. I can combine like terms. And now I can go ahead and solve this thing. I'm going to subtract the 200 from each side. And divide by the negative 19. And so when that's all said and done, what I end up with is that y equals, it's going to give me a 7. And now I have to plug that back in over here. I say, okay, let me plug that 7 back in. And I can just hit the buttons on my calculator for that one if you want. And that gives me a 4. So now back to the interpretation of this thing. So the senior citizen tickets, were $4 each. They must get a discount. And the child tickets are $7 each. Make sure you go back and interpret these things and you understand which variable is which, okay? If we look at something like this guy, it says, which pair of inequalities is being illustrated by the graph? And so the first thing we do is maybe we want to just kind of break this down in terms of the two equations. So when I look at something like this guy, a vertical line right here, this vertical dotted line, remember vertical lines are always x equals a number, and this one's going to be x equals 2 to give us the graph of that vertical line. But then, of course, I want to change that a little bit.
instead of an equal sign here, so I have the x and the 2, I want an inequality of some type, and what we see is a dotted line, so I know I'm not going to have an equal to condition. And when I look at which side of this thing is shaded, well, I'm shaded below. I'm shaded the values less than that value for x, so I'm going to say less than 2, okay? And so right away, that kind of narrows this down a little bit. I can eliminate this guy. The rest of them have the correct equation for that vertical line. Now I'm going to break this down and say, okay, let's look at this guy. Let's look at the diagonal line. And you'd probably do this. You'd probably say, oh, that's y equals. Well, that's going to be a 1x plus 2 in terms of slope-intercept form. And then, of course, I could replace the equal sign and say, well, this is going to be an inequality. I've shaded below this, so less than. And it's a solid line, so it's going to be less than or equal to. I wasn't happy with that symbol that I just did. Okay. And so now from here, when I look at this doesn't match any other equations. Well, because it's in the wrong format. And so here I would subtract the x from each side because the rest of these are in standard form. So I've got negative x minus y, plus y is less than or equal to 2. This still doesn't match because the rest of these have positive x values. So let's divide by a negative 1. Let's get a positive x value. I'm just trying to match the formatting of the question. So we got x minus y is greater than or equal to negative 2. Because I divided by a negative, I have to flip the inequality sign. And so as I look across here, it looks like this is the one that matches, okay? The other option would be to go ahead and start graphing each of these, and you'll find out, like, when you graph this one, it doesn't match the line that's on the graph. When you graph this guy, it doesn't match the line that's on the graph. This is the one that matches the line that's on the graph. So you could go through and just graph each of them until you find the one that works, okay? Look at this. It says state how many solutions for each system. And really, the way to do this is just to solve each of these systems. So like when I look at this first one, I'd probably solve this one by elimination. Everything's lined up, and it's really easy to multiply to eliminate one of these. So I'm going to eliminate x, and to do that, I'm going to multiply the second equation by 2. So the first equation stays the same. The second equation, when I multiply by 2, gives me this. Because again, the idea is additive inverses in front of one of your variables. I have additive inverse in front of x. Now I can add these together. The x's cancel out. And then here I get a negative y equals a negative 14. I'm going to divide each side by a negative 1. So I get y equals 14. Now I have to plug this back into one of these things. So I'll plug it back into this second equation. And when I solve this, I subtract the 14 from each side, divide by the negative 1. I get x equals 15. Okay, and so I've answered the question that the solution is this, but the question really asks how many solutions are there? Well, yeah, this is the solution. And you can see there's just one solution for this one. Okay. This second one, same kind of thing, except this time I'm going to do substitution. I'm just going to solve this thing. Right here, y equals this thing right here, so I can plug that in for y in the second equation. Okay, so 4x plus, instead of y, I'm going to plug in the negative 4x plus 2. And now I simplify, I solve for x. Well, but what happens here, I combine like terms, and I end up with just a 2 over here, so I get 2 equals 2. Well, in a system of equations, if I end up with a true statement like this, it means there's infinite solutions. Okay. And then the third one, again, same thing. I'm going to solve this thing. Once again, substitution's probably the route to go here because y equals this guy right here. So I can plug that in for y in the first equation. So in that first equation, I replace that y with a 3x minus 7. And now I simplify by combining like terms. I get a negative 7 equals 2. And this is a false statement. So when there's a false statement, I say it's no solution. So there are no solutions for this one. Okay. So when we get an actual answer, because it's one ordered pair, it's one solution. The second one, true statement, it's infinite solutions. A false statement is no solution. Okay. This next one, it says, is 4-1 a solution to the system of equations? Remember, for something to be a solution to a system of equations or inequalities, it has to work for all of the equations or all of the inequalities in the system. So this one, I just plug it into each of these. So that first one, I plug the 4 in and the 1 in. Again, use parentheses when you plug things in. I simplify to see if this is true. I get 4 plus 5 equals 9. So 9 equals 9, and that's a true statement. But it's not enough to be true for one of the equations. It has to be true for the other. So I'm going to plug it into the next one. And so here I get 16 plus 17 equals 17. And I add these guys together, and that gives me a 33. And so 33 equals 17. Well, that's a false statement. And so because this is false, even though the first one worked, it's not a solution to the system because it didn't work for all of the equations in the system. So I'm going to say no for this one. Okay. If I look at this, it says describe the graph of a system of equations which has each of the following. So one solution, two solutions, infinite solution, or no solution. Remember, when we're graphing, the solution to a system of equations is where the graphs intersect. So if there's one solution, it means there's one point of intersection. So the graph might look a little something like this. Here's my XY coordinate grid. And maybe I have two lines that cross at one spot. And so this would be one solution because they intersect at one spot, okay? And so describing the graph is just two graphs that cross at one spot. Two solutions, well, I have to have two answers, which means I need 2 points of intersection. So I need a graph where they cross at two places, all right? For this, I could have something like maybe an absolute value equation. If I had an absolute value equation that looked like this, and then I had another line that looked like this has 2 points of intersection, okay? They intersect at two different places, all right? And there are other graphs that maybe you can think of, maybe a parabola, which we haven't done this year, but you might remember from previous years, okay? And so it's just the idea that to have two solutions, they have to cross at two different places. Infinite solutions for this one. Infinite solutions would be if it's literally the same equation twice, okay? So if I had the same equation twice, in other words, one equation looked like this, and the second equation was the same thing on top of that, well, then they would have all of their points in common. There would be an infinite number of solutions, okay? And then no solution, again, the intersection is the solution. So if there's no solution, it means there can't be an intersection. So what I'm looking for here is parallel lines, okay? If I have parallel lines, they're never going to intersect, and therefore it's no solution. So it's just that idea of tying this idea of systems of equations to graphing and what that relationship is, okay? If I look at this one, I want to graph the inequality this time. So again, I graph the linear component. I think about this thing not as an inequality. If I just think about this as y equals a negative 2x plus 4, I would plot the y-intercept of 4 and then a slope of negative 2. And because there's no equal to condition this time, I would use a dotted line for this thing. Remember, solid line for an equal to, no dotted line for no equal to. And then I have to shade one side or the other. When y is by itself, we can use a shortcut. We can just say, oh, y is less than this line, so I shade below the line. Or we can test a point. You test a point like 0, 0, and you get 0 is less than 4. And that's a true statement, so I shade where 0, 0 is. Okay, so I shade underneath this thing. That was terrible. I went right over the line, a little carried away. Okay. And if I'd got a false statement for 0, 0, then I would shade the opposite side of the line. Okay, so process of elimination. And then it asks the question, state one solution to this equation. Well, you could say, well, I used 0, 0. That was the one I plugged in, so 0, 0 is a solution. But really, anything in the shaded region would be a solution. So like negative 3, 2 would be a solution. Okay, negative 4, negative 1 would be a solution. So any ordered pair from this. So you could pick an infinite number of ordered pairs here that would work for this thing. Okay. All right, in this one, we want to simplify this radical, and this one is a square root. So I'm going to start with the number, the coefficient to 24. And because this one is a square root, I'm looking for perfect squares that divide evenly into 24. And the perfect square that divides evenly into 24 is a 4. 24 is the same thing as 4 times 6. And now what I'm going to do is I'm going to take the square root of that, of each thing that I know how to take the square root of. And so that starts with the 4. Well, the square root of 4 is a 2. So I'm going to put a 2 on the outside. And what happens is the 6, since I don't know how to take the square root of a 6, and there's not an exact value that I get when I take the square root of 6, that one just stays underneath the radical. Okay, now I'm going to move on to the variables. Remember, with a square root, there's a little 2 right out here. It's part of the symbol. We don't typically write it. But our rules for exponents are when we divide, or when we take the square root, we divide those exponents. And so here, when I take the square root of x to the 4th, I divide that 4 by 2 and I get an x squared. Okay, and that goes on the outside. And then likewise, when I do the square root of y to the 9th, I divide that by 2. However, we only want to divide out the whole numbers. So I basically look at it this way and say 2 goes into 9 4 times. So I put a y to the 4th with a remainder of 1. So I put a y to the 1st left over underneath the radical. And that's it. Okay, and so I'm just dividing what divides out evenly. I divide a 4 out evenly, but then there's a remainder of 1. Okay. The next one, same kind of thing, except this time it's a cube root. So I'm looking for perfect cubes that divide evenly into 24. And so perfect cubes, that would be an 8. So that's 8 times 3. And now I take the cube root of each perfect cube. So here the cube root of 8 is a 2. So I put a 2 on the outside. Once again, the cube root of 3 is not something that I can easily do. So I just leave that 3 underneath. And now the variables, I do the exact same thing. I divide by the 3 this time. And so here, 4 divided by 3 is a 1 with 1 left over. So I put an x to the 1st on the outside. That was the division part. The x to the 1st on the inside is the remainder. And then here, the y to the 9th, when I divide that exponent by 3, it gives me y to the 3rd without any y's left over. So that's it. Okay? If I look at the next one, remember we used to, back in the day, we would say the square root of a negative can't be done, but now in Algebra 2, we've introduced this idea of imaginary numbers, okay? And the definition of an imaginary number is the square root of -1. The square root of -1 is I, it's the first imaginary number. So anytime we see a negative under a square root, I say, you know what, that, when I take the square root of that negative, it gives me an I value, okay? And we use a cursive I to signify that it's an imaginary number. And now separately, I'll take the square root of 81. Well, the square root of 81 is a 9. So I end up with 9i, and that's it, without anything left underneath. Okay? The square root of a -50, I start off the same way. I say, hey, the square root of a negative value is an I, so I put an I on the outside. But then the square root of 50, because I can't just readily take the square root of that, I have to do the same thing that I've always done. I have to break it down into perfect squares. And so 50, well, that's a 25 times 2. Okay, and so now the square root of 25 is a 5, so I'll put a 5 on the outside. It joins the I, and now the 2 is still trapped, and that's it. Okay, so I'm breaking this thing down into perfect squares. I'm taking the square root of each perfect square, okay? And in our book, a -1 is now a perfect square. It comes out as an I, okay? When I look at this guy, I want to solve this thing, and solving something like this is really just a matter of working backwards sort of operations and undoing the operations as I go. And the thing you have to keep in mind is this square root, there are parentheses implied here because that square root it's the square root of that entire 3x minus 2. That 3x minus 2 is in parentheses. So I start outside the parentheses, outside the square root, and I undo the addition and the multiplication. So to undo this adding 5, I subtract 5. I'm working backwards sort of operations. And now once again, this is still trapped underneath the radical. It's parentheses, so I'm saving that for later. So here that gives me an 8. Now I undo the 2 that's also outside the radical. So to undo multiplying, I divide each side by 2. And now I'm ready to undo the actual radical. I have to undo that square root because, again, this stuff down here is still trapped in parentheses. I have to save that for last. So to undo the square root, I have to square each side. Roots and exponents cancel each other out. So here, the square root and the square cancel each other out. So I'm just left with the 3x minus 2. Over here, 4 to the second power is 16. And now I continue to solve this thing. Now I'm left with what was in the parentheses. I undo order of operations by adding the 2 to each side. And dividing by the 3. And it is important with these, I can get extraneous solutions. Make sure you plug it back in and check it. Plug that 6 back in for x and make sure it works. This one does. Okay. If I look at the next one, same kind of thing. I'm working backwards sort of operations. So I'm going to undo addition and subtraction, then multiplication, division, then exponents and roots, then parentheses. So here I undo the subtraction by adding 12 to each side. And now I undo the multiplication by dividing each side. And so again, I'm undoing everything that's outside of the parentheses. Well, I still have that squared is outside the parentheses, so I'm going to undo that by taking the square root of each side. To undo an exponent of 2, I use a root of 2, just like it did in the previous examples. The root and the exponent cancel each other out, and I'm left with an x plus 6. But then there's one extra little stipulation here. Whenever I take the square root of each side, I have to do plus or minus the value over here. So this is a plus or minus 3 when I take the square root of that 9, okay? I have to do the plus or minus because of that technicality with absolute value, okay? We just have to remember whenever we take the square root of each side, it's plus or minus that value. And now I'm going to subtract that 6 from each side. And really, this means two things. When I look at this, I have a positive 3 minus 6, and then I have a negative 3 minus 6. So positive 3 minus 6 is negative 3. Negative 3 minus 6 is a negative 9. And those are my two answers. I could plug each of those back in, and they'll both work. Okay? If I look at this one, it asks me to multiply and simplify. And remember, when we're multiplying things that have multiple terms, I have to use my distributive property. And a lot of times I have to use my distributive property more than once. So in this one, I'm going to distribute the 2x. So I'm going to distribute that to all three terms over here. And when I do, that's going to give me a 2x to the third. Remember, we add the exponents when we multiply, plus a 4x squared, and then minus an 8x. And now I'm going to distribute the next term. I'm going to distribute that positive 1. So I'm going to distribute that plus 1. That gives me a plus 1x squared plus 2x and a minus 4. And now I just combine like terms. The x squareds are like terms. These guys are like terms. And everything else just tags along for the ride. So 2x cubed plus 5x squared minus 6x and a minus 4. And that's it. Okay. The next one is the same kind of thing. I just have to rewrite this first. If I have something squared, it means that thing times itself. I can't just square each piece. I literally have to do the 4x plus 5 times itself. So 4x plus 5 times 4x plus 5. And now once again, it's my distributive property. I distribute the 4x to each of these. That gives me a 16x squared and a plus 20x. And now I have to distribute the next term, the 5. So I distribute that 5. That gives me a plus 20x and a plus 25. And now once again, I combine like terms. So that's a 16x squared plus 40x plus 25. Okay. If I look at these guys, it says to solve each and leave your answers as fractions. Well, for these ones, I want to solve, and really I'm using the zero factor property to solve. This is the same thing I do when I solve by factoring, okay? Typically, I factor the thing and then set each factor equal to 0. Well, this is already factored for me. If I have two things being multiplied, this guy times this guy, and it equals 0, what that means is one of those things has to equal 0. Again, it's that idea if I have a times something and it equals 0, you automatically know that that question mark has to be a 0 in order to make the whole thing 0. Or the a could be a 0 to make the whole thing 0. But that's the point here. If two things are being multiplied and equal 0, it means one of those things is 0. Either the x minus 2 is a 0, or the x minus 3 is a 0. So I set each of those equals 0. Now I just solve the two equations that I have. I add 2 to each side. That gives me x equals 2. Here I add 3 to each side, and I get x equals 3. And that's it. Those are my two answers. If I look at the next one, same kind of thing. I have two things being multiplied. It's x times this 2x plus 9. So either, if those multiplied together equal 0, either the x equals the 0, or the 2x plus 9 equals 0. And now I solve each. This one's already solved, x equals 0. This one, I'm going to subtract the 9 from each side. and then divide by the 2. And again, I'm just going to leave this as an improper fraction. It's x equals a negative 9/2. So here's my two answers, x equals 0 and x equals a negative 9/2. And that's it. If I look at the next one, same kind of thing. These two things multiplied, this guy times this guy equals 0. So either the 2x minus 1 equals 0, or this 5x plus 4 equals 0. And I solve each. Here I add the 1 to each side. That gives me a 2x equals 1. And then I divide by the 2. Over here, I'm going to subtract the 4 from each side. And then divide each side by the 5. And that's it. I leave them as fractions or improper fractions. But the point is the zero factor property. When I have two things multiplied equals 0, I just say, hey, one of these things equals 0. So set them each equal to 0 and solve each. Okay? And now applying that essentially the same thing here, I want to solve by factoring. Well, I just factor each of these. It's already equal to 0. I'm going to factor this and then set each factor equal to 0. Okay, so I have a couple extra steps right before I do the thing that I just did in the previous examples. So this one, when I see this, this is a difference of squares. And, you know, one of the things we always look for is we look at the number of terms. If I see 4 terms, I go right to factoring by grouping. If I see 3 terms, I build a bridge. If I see 2 terms, I look for special cases, and really for all of those, I should always look for greatest common factor first. This one doesn't have any greatest common factors, but 2 terms, I look for special cases. My only special case that we know so far is difference of squares. And we recognize that by seeing, okay, here's a perfect square minus another perfect square, okay? That's why it's called difference of squares. Difference means subtraction. So I have subtraction of 2 perfect squares. When I have a difference of squares, it automatically factors into conjugates. So 2 binomials that are the same but with different signs, one's a plus, one's a minus. And to find the values, it's really just the square root of these things. The square root of x squared is an x. The square root of 81 is a 9. And so when I see a difference of squares, 2 perfect squares being subtracted, it automatically factors into conjugates, one's a plus, one's a minus. And now I can set each factor equal to 0. Either the x plus 9 equals 0, or the x minus 9 equals 0. And now I solve each. So here I get a negative 9. And here I get a positive 9. Okay? And here's the thing. There are other ways to solve this one. Like you could add the 81 and just take the square root of each side. You just have to remember to do plus or minus that square root. So it's plus or minus that 9, just like we got here from factoring. Okay? This one, once again, I'm going to look at the number of terms. I see 3 terms. My go-to method with 3 terms is to build a bridge. So building a bridge means first number times the last number, first coefficient times the last coefficient. That's a negative 8. And now I need 2 numbers that multiply to a negative 8, but add to this middle term the negative 7. Okay? And those 2 numbers, those 2 magic numbers, are going to be a negative 8 and a positive 1. And so now I split up that middle term. Remember, sometimes we can use a shortcut here. If the a value is 1, if I had a 1 out front right here, I could go right to the factored form and just say, oh, x minus 8 and x plus 1. But I can't do that because there's a 2 out front. So because there's a 2, I can't use my shortcut. I have to split up that middle term into a minus 8x and a minus 1x. And now I have to factor by grouping. I replace that minus 7x with a minus 8x and a plus 1x. And now I factor by grouping. I group the first 2 together. I group the second 2 together. Out of the first group, I can factor out a 2x. That leaves me with an x and a minus 4. Out of the second group, and with factoring by grouping, you have to factor something out, even if it's just a 1. I can factor out a positive 1. That leaves me with an x minus 4. And now the goal of factoring by grouping, I need to get the same thing in each of these parentheses. And I have that. So my 2 factors are the thing that's outside, the 2x plus 1, times the thing that's inside, the x minus 4. And see, now I'm to that step that I was in the previous couple examples where, hey, 2 things multiplied equals 0. So either the 2x plus 1 equals 0 or the x minus 4 equals 0. Okay? And if I solve each of these, that's something you should be able to do at this point. The first one, I subtract the 1, divide by the 2, I get a negative 1/2. The second one, I add a 4 to each side, and I get x equals 4. And those are my two answers. Okay? If I look at these guys, it says solve each. So method of our choice here, it just says be sure to use the quadratic formula for at least one of these. Quadratic formula is just something that you should have memorized. It's important to be able to do that, okay? So the progression that we go through, once again, I see 3 terms here. The first thing I always check with a quadratic is I always build a bridge. I see if I can factor. So here I build a bridge. That's a negative 10. And now I need two numbers that multiply to a negative 10, but add to a negative 3. Well, that would be a negative 5 and a positive 2. And the fact that I can come up, that those two numbers exist, that I can come up with those two numbers, tells me that this thing can be factored. And when I look, there's a 1 out front, so that means I can use my shortcut for factoring. So this minus 5 and plus 2 automatically becomes an x minus 5 and an x plus 2. So I go right to the factored form. And again, you can only use that shortcut when the a value is 1, when the leading coefficient is 1. And now I set each factor equal to 0. X minus 5 equals 0. X plus 2 equals 0. And I'm going to add the 5 to each side. Subtract the 2. And here's my two answers. Okay. And here's the thing, you could solve this one by something like the quadratic formula. You just have a lot of simplifying to do, okay? So keep that in mind. You could use the quadratic formula every time, but make sure you simplify, simplify, simplify as far as you can. You should get to these same two answers, okay? This one, same kind of thing. I build a bridge. So I build a bridge that gives me a negative 12. Two numbers that multiply to a negative 12 but add to a positive 1 are going to be a positive 4 and a negative 3. And the fact that those values exist tells me that I can use factoring to solve this one. And so for this one, I could split up the middle term and factor by grouping. I can't use the shortcut because there's not a 1 out front. So I split up the middle term, and now I group. I factor by grouping. Out of the first group, I can factor out an x. That leaves me with a 3x plus 4. Out of the second group, I can factor out a negative 1. That leaves me with a 3x plus 4. And now my two factors, once again, are an x minus 1 and a 3x plus 4. And so I set each factor equal to 0, x minus 1 equals 0, 3x plus 4 equals 0. And once again, I'm going to skip the couple steps for solving this one. This one ends up equaling a 1. This guy, when I solve, ends up equaling a negative 4/3. That's it. And for this one, let me just show you real quickly for those of you who like the quadratic formula. If you do the quadratic formula on this one, x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So x equals opposite of b. Remember, for the quadratic formula, my a, b, and c values are these guys. They're the coefficients. It's the 3, the 1, and the negative 4. That's a, b, and c. Okay. And so for this one, the opposite of b is going to be a negative 1 instead of that positive that's here. Okay. Sorry, I'm just trying to clean that up a little bit so we can see what we're working with. So opposite of b plus or minus the square root of b squared minus 4 times a, which is a 3, times c, which is a negative 4, all over 2 times a, which is once again that 3. And now I just have to simplify. I have a ton of simplifying to do typically when I do the quadratic formula, and it could be solved by something like factoring. I just have to make sure I continue to simplify till I can't simplify anymore. So here that gives me a 1. That's a plus 48 when I multiply that out, all over a 6. And I keep going. I continue to simplify because I can. And so now what I have here is I've got negative 1 plus or minus the square root of 49. Well, the square root of 49, I can take the square root of that. That's a 7. So I get negative 1 plus 7 over 6. And what that means is I have to do this twice. I have to do negative 1 plus 7 and then divide it by 6. And then negative 1 minus 7 and divide it by 6. Negative 1 plus 7 is a 6. Divided by 6 is a 1. So x equals 1 is one of my answers. Negative 1 minus 7 is a negative 8. Divided by a negative 6. Well, negative 8 over a negative 6, well, that reduced it to a negative 4/3. So that's my other answer, -4/3. And that's it. I get the same answers. It just requires a little bit more simplification. Okay? If I look at this guy, once again, I start off by building a bridge. I always check building that bridge. So -8. Two numbers that multiply to a -8 but add to a +3. Well, there are no two numbers that multiply to a -8 but add to a +3, which means this one cannot be factored. Okay? Factoring did not work this time. So I have to use a different method. Okay? And so for this one, the next method that I tend to check is completing the square. But completing the square is only good when you have an A value of 1 and a B value that's even. And this time I have a B value right here that's odd. And so because I have an odd B value, this one is not going to be a great one for the completing the square. Okay. And so what I'm going to do is I'm going to move on to my quadratic formula then. Okay. So for this one, quadratic formula, opposite of B. So the opposite of B plus or minus the square root of b squared minus 4ac. A is a 1 this time. C is that -8. And it's all over 2a, which is a 1. Okay? And now again, simplify, simplify, simplify. I have to continue to simplify this thing. Here, that gives me a 9. This is going to give me a +32. I continue to simplify. I made that square root a little bit bigger than I needed to. So I continue to simplify. That's a 41 over 2. I look for perfect squares divide evenly into 41, and guess what? There aren't any, which means this is literally my answer. Okay? And if this was like a word problem of some type, I would probably plug this into a calculator. All right. But when I want the exact value, I just leave it in this kind of a big fraction kind of wonky format. Okay. If I look at this one, once again, I would start by building a bridge. I would check factoring. Factoring is always the easiest method if it works. So I build a bridge, two numbers that multiply to a -5 but add to a +2. Well, once again, that's not going to happen. There are no two numbers that multiply to a -5 but add to a +2. But this time I have an A value of 1 and a B value that's even, so I can do completing the square. So completing the square, I create space. I'm going to move the constant term out of the way. And now I complete the square. I create a perfect square trinomial by doing b divided by 2 and squaring it. So if I take that middle term, the 2, divide it by 2 and square it, it gives me a 1. So I put a +1 here. And the thing is, whatever I do to one side, I have to do the other side. So I have to put a +1 on the other side as well. And now I continue to simplify. The whole point of creating this perfect square trinomial is because this, the x squared plus 2x plus 1, will factor into a binomial squared. And just think about it this way. If I build a bridge, two numbers that multiply to a 1 but add to a 2 would be a 1 and a 1. In other words, this factors into an x plus 1 and an x plus 1, which is x plus 1 squared. And now what I can do here is I can solve by taking the square root of each side. And so I take the square root of each side. Remember that when you take the square root of each side, you have to remember to do plus or minus that value. So that's plus or minus the square root of 6. And then continue to simplify. Are there any perfect squares divided evenly into 6? No. So I finish solving for x by subtracting that 1 from each side. Okay. And I write my answer in this format. I say x equals -1 plus or minus the square root of 6. And that's it. Done. Okay. You could do this one by the quadratic formula as well. Really, the big difference is if you do the quadratic formula, you just have a bit of simplifying to do with the square roots, okay? I'm going to have to simplify the square root. I'm going to have to do a little bit of division and reducing fractions to get to this point, okay? But you'll still get there if you do the quadratic formula, okay? This one is a little bit of a tricky kind of a challenge question. It says write the standard form of the equation of the quadratic with the given zeros. In other words, this time I'm starting with the answer and I want to work my way back to the original problem, okay? And so for this particular one, if I start down here with x equals 4, if you think about it from the perspective of solving by factoring, it means the previous step I probably had something equals 0. And in order to get x equals 4, the thing that I would have to have is x minus 4 equals 0, if that makes sense. Kind of just working backwards, okay? Likewise, if I had a value of x equals a -5, The previous step would have been that I had to have x plus 5 equals 0 in order to solve and get x equals a negative 5. And then think about the process of solving by factoring. I set each factor equal to 0, meaning that the previous step would be x minus 4 times x plus 5 would have to equal 0. Okay, I would have to have those two factors multiplied to equal 0 before I split them up to make each one equal 0. And now the previous step before that would be what I would have if this wasn't factored, if I were to kind of multiply this back out. And so if I do my distributive property or FOIL here, I end up with x squared plus 5x minus 4x minus 20 equals 0. And the previous step to that would be x squared plus x minus 20 equals 0. Okay, I'm working backwards to the unfactored form of this thing. And so the equation that I must have started with was x squared plus x minus 20 equals 0. If that makes sense, okay? And here's the thing, that is a challenging type of question, but if you understand that, then you truly understand the process of solving by factoring, okay?